Hi guys, so today we are going to be creative again, and what we will do is we will build a real new product which can then also be purchased. So I have recently designed a new current sensor board. I told you this in the last video because I have built in there this sensor here, which is from China, and I'm not fully happy in how this is built. So I use this opportunity, what I have done already some other times, that I have built my own electronics, and this is going under a sort of improved Chinese basic electronics, right? So you can buy usually all this sort of stuff. I'm only making this, of course, which I'm also using here for my power projects, and you can buy of course all these kind of things cheaply in China or Amazon, wherever, which all have the same origin anyway. And they are always, of course, cheap, but sometimes they are not very well thought through, and the main motivation is really just to be cheap. So that's of course what DIY people also need. But at some point, when you're starting to have your own DIY systems, you also want to have some quality components used. The items which I have built until now, one is my first one. It's quite a unique, you cannot buy anywhere usually. This is a long duration watchdog, which is very nice when you have Internet of Things, something connected to the web. You need something what is taking care, a hang microcontroller for example, but giving it quite some time. So this is about 30 seconds watchdog. And then the first of my items which was made in the improved series of Chinese electronics was my relay boards. This one also quite unique. It's I2C, I2C 12 channel board, so only 4 wires in, and you have 12 relay channels. So also the best components used. And today we are going to build a current sensor based on the ACS758 chip. This is a Hall sensor. It looks like this here. We will take a look on all of these shortly. And this is also great because it's bi-directional. So what we need in our battery applications, of course, we want to measure charging and discharging currents, and all this in a nice form factor. This is already a finished board, and yeah, we are going to look what it can do and how especially it is behaving with noise and ripple. Yeah, and for all these, today we have a new helper, my oscilloscope. I got a Hantec DSO 2D10, and this will be the first time we are going to use it. Let's go to the power wall, and I want to show you what the challenge actually is when it comes to these sort of measurements in a very dynamic power application, when you have AC, DC and all these sorts working together. Before we are looking into the DIY sensor, let me show you actually the challenge which you have in such a power application when you are trying to measure DC current in an AC coupled system. What actually is the AC side doing to your DC side? For that I have here my oscilloscope. I have the Chinese current sensor. The sensor does have a low pass filter on the board, but that one was actually set to extremely high frequencies, and I have replaced a 220 picofarad capacitor with a 1 microfarad. So that has eliminated already the high frequency noise, which was especially at a peak somewhere around 200 kilohertz, and then another peak at 3 megahertz. So those are gone. The only thing what is left is the AC ripple on the DC. And how does that look like? So if we look at the current measurement here, the controller says we have somewhere around 36 amps. My meter says 33 amps. So the controller is about 10% above the measurement of the meter. And while the meter is pretty stable, you can see that here the controller, the amperage will go up and down quite significantly. Why is that? Let's look at the oscilloscope. So we have here the DC output of the sensor. The zero line is 0 volts. We have DC and overlaid, as you can see now, AC ripple. Let me press here the stop so that this is not jumping around. So what exactly do we see here? So this in general, DC should be actually a straight line here, of course. But why do we have this wave on top? This is the ripple caused by interaction of all these AC devices on the DC main bus. So I have chargers on 2 phases which are taking away power. And this you can actually see in form of the ripple. We have one peak, we have another peak, and then we have the third one, which is the negative peak. This will be the phase where nothing is taken off, and then another one which is not using so much energy, and then that one which is most used. And this will cause this kind of waveform here. I have measured this out with the cursor here, and if we look here from trough to trough here with these 2 cursors, which you might see here, we have a ripple frequency of 640 Hertz about. That will be a harmonic. So this is actually what we need to get rid of with a filter. So ideally we want to get this frequency filtered out, so that at the end only the DC part remains, and we can then make a stable measurement with our current sensor. Let us take a look first what kind of products do exist around the ACS758 hole sensor. So this is the bare hole sensor. You can see my hand is quite a big chip, and they do exist in many different variations. You can have different formed legs. This one is made to be put in a PCB. They exist in unidirectional and bidirectional versions, and then they have 50, 100, 150 and 200 amp chips as well. So this one is a bidirectional 100 amp. So this in principle is already a finished application. The only thing what would be required is a decoupling capacitor between the VCC and the ground pin. But then you can already take an output signal of this chip and use it as a current value. The issue with that is, of course, that the signal will not be clean, and you saw that before when we were looking at the ripple at the power wall. But nevertheless, if you are just measuring a very stable, clean DC from a DC power supply, it would already work. So now there are products which you can buy online, AliExpress, Amazon, wherever. These are simple breakout boards which essentially only have the chip on a small PCB. Then there are also a few components on the back side, even a op amp here, but they are not doing anything other than creating a buffer, a second output which is buffered by a op amp. So if you have impedance problems with your analog to digital converter, this could help you out in this case. But otherwise nothing else than decoupling capacitor, a little bit of low pass filtering, and that's already it. Something like this costs $3.50, but you can already see, imagine this is a 200 amp or even a 100 amp sensor, and this is only going to a small hole here where you then directly connect your wire, or however, I cannot even imagine how this could really work well. And yeah, but there's no way that you could connect a battery cable which is like more than 10 square millimeters. For a 200 amp application you would need a 50 square millimeter copper cable, so just tell me how you could connect this to such a breakout board. But anyways, I saw this already even on YouTube, some people using like this. I would highly recommend not to do it. Then I found a product also on AliExpress which is quite similar to that one what you saw before. The price is much higher because they have redesigned the electronics part a little bit, but still in this version also just a second output which is going via op amp just to improve the impedance. If you have an issue with this, this is also just a buffer. So much higher price, but nothing different to the cheap board. Still as well, two small holes to connect a big cable. How would that work? Well, I don't know. So then we already have the board which I have then finally used now in my power wall for some times. I bought this one because it has now really nice terminals, M6 screws to connect big size cables as well, which have cream plugs. These terminals actually are rated up to 120 amps. You can buy this board as well for currents up to 200 amps, but this is against the rating of those components. Otherwise, we have double-sided copper here. This is going here to the chip, and then we have some electronics here. We will talk about this just in a minute. This is now my design. We have a similar one here. We have the high quality terminals, screw terminals. You can connect almost any size of cables to this. Then the current sensor and as well an electronics part. Let's talk about the differences in that electronics part. What did I not like on the Chinese version? What did I change from my improved version? These are now the two sensors. This one you can buy for $25 US, so it's not cheap for Chinese standards. What does it have here on this end? So first of all, the main part, so your current sensor, the output of the sensor is just going through a passive low pass filter. So this is designed to remove some noise, but in the factory version there is a noise filter here which is set to a cutoff frequency of 7 megahertz. That is extremely high, so it is really only filtering out extremely high noise. But in my power wall I saw about 3 bands of noise, regular noise, so the ripple, and 2 bands of other noise, and they have been all far below the 7 megahertz. So that's why I have actually changed that low pass filter. I have replaced the 220 picofarad capacitor of the filter with a 1 microfarad, and that has then changed the cutoff frequency to around 1600 Hertz. And yeah, we will talk about low pass filtering. Then the other part here on this sensor is a op-amp comparator circuit. So you can set on this trim potentiometer a certain current value, and that will trigger a digital output from low to high or vice versa. When the current is exceeding a certain value, you will get a signal. So in my case, I do not need this, and I find this also a little bit unnecessary, because what are you doing with this sensor signal? You are going to an analog to digital converter, and that one is read by a microcontroller. So to include a comparator, this requires only 1 or 2 lines in programming for the sketch in the microcontroller, and you can already have a comparator there. It's just like a if-then sentence there, and you have already set the comparator inside the code. The third part here is actually external DC input. You can put like 7 until 24, or here actually it says 28 volts. Connect here via 1 pin, and then you have here a voltage regulator down to 5 volt, which will give external power supply to our chip. This is actually as well not really necessary in my opinion, because the chip actually can run on any VCC supply voltage between 3.3 volts and 5 volts. So the two major voltages which are used for electronic circuits and microcontrollers and the analog to digital converters are already covered. So having this chip extra supplied with another power source is absolutely not necessary, because the chip itself is pulling almost no current, so nothing of this is actually requiring really much current. So that's why in my power wall the only thing what I have used of this configuration was just current measurement, and the other two parts have been just idle. So what did I change on my design? We again have the current measurement, but this time it is going straight into an active low pass filter. So this is covered by this op-amp here, and there are several advantages of using active low pass filters in comparison to an passive low pass filter, and one of it is because of the impedances, input impedance and output impedance of an op-amp. This filter is set to a cutoff frequency of 1.6 Hertz. So this will eliminate any AC in the DC output here. Then the second part here, also a voltage regulator here, same as on the other, but it's doing something completely different. This one takes the 5 volts here, or 3.3 volts, whatever you use as your VCC for this board, and is creating a reference voltage of 1.5 volts. Why you need a reference voltage is subject of another video. It has a lot to do with analog sensors and how you counter VCC instability which you might have in your main circuit. Right, so this is now a measurement setup. Chinese board first. I have here from our signal generator injected into the output of the sensor. The sensor is not powered up, and at the same point I took probe number 1 to channel 1 of the oscilloscope. And the other probe is on the output of the board, which would go to the analog to digital converter. Channel 1 before the filter, channel 2 after the filter. So let me show you what I have set on the oscilloscope, and then we do some measurements. So on the oscilloscope now, all channels and signal generator is turned on. I have on the vertical, I have 1 volt per division. So what I am simulating here is an input signal. We can also look at that on the wave generator. A sine wave of amplitude 300 millivolt overlaid on a DC of 2.5 volts. 2.5 volts would be the output of the bi-directional sensor when there is no current flowing. So this is a sort of our simulated AC ripple on the DC. The frequency is set to 20 Hertz. So this is, as you can see, yellow line, channel 1 input, green line. They are on the same size and same position. They are overlapping each other. So now what I can do is start cranking up the frequency, and then we will see when the green line, the green wave, will start to lose some amplitude. So let's check that. And cranking up frequency. So we know our cut-off frequency here should be 1600 Hertz. Let's do it this way because we can crank up much faster at the moment still. So this would now be our cut-off frequency, and I think we can already start seeing that the amplitude of the green wave is already starting to decrease. I think you can clearly see that the amplitude of the green signal of the output is already going down. So we are at 6300 Hertz, so clearly above the cutoff frequency, and it's really getting reduced. The low pass filter is flattening out our ripple as it is now at 30 kilohertz. It is mostly gone. Right, now I have one of my boards here. I had to build this board now quickly and only have the components of the active filter on it. Because the problem is, the active filter, of course, this is supplied by the power here, and once, if the board is completely populated, if I turn on the power, then the sensor is also powered on, and it would completely overwhelm the signal generator. So in order to test only the filter, I only had to finish this part of the board at the moment. So now we can test it. On the oscilloscope now, the board is unpowered yet, 5 volts. And now you can see the op-amp is starting 10 Hertz already, but you know our cutoff frequency is 1.6 Hertz and the green line is already completely straight. But as you can see perfectly, input ripple is completely disappeared, and that's already on 10 Hertz. So yeah, if I am cranking up the frequency here, the only thing what's gonna happen is that there just will be no AC signal left anymore at all. So even with 50 Hertz, let's say we have a 50 Hertz one-to-one ripple, you can see an absolutely straight output DC signal. So the filter, active filter, works absolutely perfectly. Let's briefly talk about reference voltage, but this will be a topic of a separate video because this is something very important when it comes to analog sensors. The second part of my board is a reference voltage source. A reference voltage source is a source which derives from our main voltage here, which will be 3.3 or 5 volts. In my case, I have here 5 volts now, and this reference voltage is given by a linear voltage regulator, and it can output its 1.5 volt in this case, as long as the voltage which is coming in is more than 3 volts. So whenever, doesn't matter how the voltage, input voltage varies, it will output 1.5 volt, and the circuit will guarantee that that voltage is given. This kind of voltage reference source can be used to check on the VCC and the sensor is giving accurate output. So let's see how much voltage it is providing. I have a test point here, and it's showing 1.527 volts on this meter here. And it doesn't matter, you can see now if I turn this down now to 4.3, 3.6, the reference voltage is always exactly very stable 1.527. I can also go a little bit higher, but that we have to be careful to not damage the sensors. But as you can see, 5.4 volts now and 1.528. This works also very nice. Okay, perfect, it works absolutely like expected. What I'm going to do now is install this sensor inside the power wall, and then we're going to take again the oscilloscope and check up about the measurement now, look at the signal, and also look if the measurement is now more accurate than it was before. Yeah, and so this is now at the power wall. I have installed my sensor. We have again current metering here. It's still the only thing, I have the other cable from the other sensor still here, which should actually be changed because that one has different wiring. But because of that connection, you will see we may have picked up a little bit noise, but that's no problem. So this is now what the oscilloscope is showing. We have clearly a straight line here. So this zigzag, that's just random noise. It doesn't hurt so much. I have here again two cursors which are 500 Hertz. So here was clearly before a big wave seen, and now there's just, as I said, this stuff. So the filter did all what it could and the ripple is gone. How is the readout now? We have now around 29 amps. Here we are at 31, almost 32, but you can see the readout is very stable. So the only thing now, this 5% difference which we have here. This was really a successful, nice test, and the product, the sensor, is working just fine. Good. So this sensor can be purchased if you're interested in something like this. I'm putting it again on the same shops which I am using here domestically in Thailand, it is Lazada, and for international shipments it is Tindie. So at the beginning there will of course only be a few pieces available, but if there is nothing on stock, please just notify me that you need something like this, and I can make it. I will slowly ramp up production if it's necessary. Good, the price for this will be just in the middle of the cheapest and the most expensive Chinese versions. So this will be $15 without shipping. The biggest problem is always shipping costs. That's why usually makers outside of China don't have much chance against the Chinese manufacturers, because they ship more or less for free. But yeah, at least here in Thailand shipping cost is very little. You can have a good stable sensor now. The calibration is done anyway in the software inside the microcontroller when you're calibrating against the multimeter. Right, so now it is showing about 5% more than the multimeter. This can just be calibrated via software. Okay, so that's so far it. There will be another video which will then show how this sensor works together with a microcontroller and how it works to compensate reading issues when there's a voltage issue on the supply rail of your main voltage, that how this works when compensating with the voltage reference, which is also on this board. I hope you found this interesting. Please comment on the down, like the video, subscribe to the channel, and I see you next time.